Hello everyone, welcome to a new video. Today we will be talking about cryptographic algorithms. So, cryptographic algorithms, these are algorithms that we use to stay um, mostly as stuff like anonymous on the internet, right? Because we don't want hackers knowing data about us when we send it through the internet, right? So when in your computer, when you send something from your computer to like a server, right? Say like YouTube or something, we want to make sure that no hacker will know what you are sending it and what it is sending back to you, right? Well, both you and the server still need to know, right? To transmit information. And so, you might have heard of this. One of the most common ways to do this is called encryption, right? So, encryption is one of the most well-known cryptographic algorithms. Basically, what it does is it takes whatever text you have, say you want to say hi, and you put it and you put a password on it basically. So like after you make some sort of password, right? This hi text turns into a bunch of random nonsense. And to decode that random nonsense, the only way to do that, to figure out the original text, is to know the password. And so then you can go from this and put the password and get into the original text, right? And this can all be done mostly with math. It's like, say you want to encode ABC, and you just turn this into 1, 2, 3 or something, right? And now only someone who knows how to turn it back would be able to turn it back, right? But this is much more secure, obviously, because we have newer systems like AES and all that can do this. Now, I do want to highlight some differences here, because there are multiple types of cryptographic algorithms, right? And there's one specific one that I want to focus on that might seem useless, right? So the most common one obviously is encryption, right? You take some text and you mangle it up using some sort of password. You send it to the guy, and that guy also needs to know the password, right? Only then can he understand that mangled up text. And so this process of making the text all mangled up using this password is called encryption, or encoding, I guess. And the process of getting the original text back is called decoding. Now, apart from encryption, right, there's also this other thing called hashing. Now, hashing is very intriguing, right, if you do not know the specific uses of it. Because what it does is very counterintuitive. It takes some sort of text and it mangles it up. That's pretty much it. There is no way to retrieve the original text back from that mangled up nonsense. And so you might think, wait, why would we ever do that? That just seems pointless. You're turning this text into that, and, well, what are you going to do with it if you can't turn it back, right? And I will highlight some uses for this. But firstly, I want to show you a small demonstration of what this looks like. As you can see over here, I've pulled up a small online tool just as a demonstration. So if so this specific thing is called the SHA 256 hashing algorithm. That's just a technical name. But as you can see, when I type something in, it turns my text into a bunch of nonsense, right? And that's what it's supposed to do. There isn't any way that we know of yet to turn this back into the text. Mainly because hashing destroys information, right? There are multiple texts that can give the same hash. So we will never get the input back. That is a very important thing. Also, there are so many of these combinations that we could not possibly find two inputs that give the same output anyways. This is what we call collision attack, and we have never been able to do this because of just how huge the state space is. But here's one thing I want you to notice. This is what hello world, when you put it through, looks like. If I just add an exclamation mark, the hash looks completely different. This is what we call the avalanche effect. Because hashing algorithms are built to make the output look completely random and nothing like the input. There should be, remember, no way to construct the input from the output. Even just small changes can completely change the hash. So you cannot say, oh, the hash is close, maybe I just have to change a few characters. Because a few characters can completely change the hash. And this has some really, really good uses. Alright, say I put... Okay, this isn't one of the main uses in computers. And this is used on your computer every day when you log in. So your computer never stores your password on your computer directly, right? If it did, that would be a huge security risk. Anybody who got your computer could easily open up your storage, and find your password in there, right? So, contrary to what you might think, your computer never stores your password, just normally on the thing. Instead, it only stores this hash. And so look, one important thing about hashes is even if it looks completely random, the same input will always give the same output. Hello, no matter what, will always give this output. On your computer, on my computer, on some other computer, even if I retype it, same output here. Right? So what your computer does is, instead of storing the password, say I put some password like ABC123. Here I have a password, right? Instead of storing the password, it stores this hash. And here's the thing, remember, there's no way to get the input back from the output, unless you just try every single input and then be like, oh, this input finally corresponds to this output. So if you have a good enough password that nobody can just try every single possible combination, you'll never be able to find the password from this, right? But obviously this is just a bunch of nonsense. How would your computer know if you typed in the right password? Well, remember, the same input's always the same output. So when it needs to know if you typed in the correct password or not, it will just hash it again and see, oh, does this hash equal the same hash that we got before when he first set his password? And if they're the same, congrats, you got into the computer. And if they're not the same, well, you don't have the same password. So yeah, that is one of the main uses for hashes. One other major use of hashes is used as a checksum. Basically, file integrity. Let me explain. So say I'm over here, right? This is me, and this is you, and we both have some huge file, say like 100 gigabytes or something. You know, most people don't have that many files with 100 gigabytes, but say we both did, right? And you suspect, wait, I think my file is corrupted. I think it's different from yours. Now, you might think, okay, how would you tell if your file is the same as mine? Right? Now, you might think, obviously, you'd have to send the entire 100 gigabytes, and then I would have to individually check the entire thing to make sure they're all the same, and then send it back and be like, oh, okay, you know, all good. But that's completely unnecessary because of hashing. The whole idea is, hashing, it takes any input and turns it into a random fixed size output. I might not have mentioned that before, but it makes it the same size as you saw in the demo previously, with the input and output in that website. You can just take this entire 100 gigabyte file and hash it into some combination of digits. And if you also hash the file and you do not get that same combination of digits, right? Then I know, okay, we do not have the same file. These are not the same files. So for this one, we'd use a common hashing algorithm usually called MD5, which is a very fast hashing algorithm, right? So hashing algorithms, there are many different ones, right? Some of them are really slow, some of them are really fast. Now you might think, why do you want a slow hashing algorithm? Use the fastest one, right? But in stuff like password storage, you want the slowest algorithm possible. Because think about it. You want the attacker to not know your password, right? So you can still find the original from the hash by just trying all the possible combinations that you can think of, and then seeing if that equals the hash. And having a slow hashing algorithm means it will be much slower to try and do that. So sometimes you want fast hashing algorithms, sometimes you want slow hashing algorithms, and so it depends, right? Sometimes you want fast, sometimes you want slow. It it all just depends, really. Now, of course, I will show you one final use for this hashing, and this one is also one that you see a lot of the times in real life. Alright, this one's a bit more niche and usually not talked about as much, right? It's not a primary example of hashing. Hashing is used in many different places, right? But you know how when you connect to an internet, a lot of the times you need a password to connect to this internet, right? By internet I mean network, sorry. So your router's over here, right? And you are over here. And you're trying to connect to your network. And it's asking you, oh, what's the password, right? Now there's a big dilemma here, right? Because maybe there's this hacker over here who's just waiting, he's listening. He's waiting for you to send the password over to the router so he can steal that password, right? But here's the thing. With hashing, we can tell the router that we have the password without ever sending the password to the router. Now this might sound impossible because how is the router supposed to know we have the password without it ever getting the password from us? But this is possible using hashing. Now, I won't go over exact technical details because this is a bit more complicated than what I'm just going to say. I'm going to horrifyingly oversimplify this. The thing is, if I just take whatever password I have, right, let's use the old ABC123, and turn it into its incredibly long mangled string, right? And then I send, instead of sending the password to it, I send this, the hash. Now remember, our router over here can take what it knows is the password and hash it itself. And once it gets the hash, it can compare its hash with my hash and see if they're the same. Then I would know the password, right? Because I can't get the hash without knowing the password. And the hacker over here will see. They will see the hash, right? But the hash is useless. Because remember, hashing is a one-way operation. You go from the password to the hash. You cannot go back. So the hacker just saw what's completely useless to it, right? But to me and the router, we both know now that we have the password, and the router allows me to connect to the internet. This is just one of the many uses of hashing that exist in modern day society, right? So what seems initially pretty much useless, like encryption seems useful, right? You take a password and then you encrypt it, and then you decrypt it later, right? But hashing, what seems completely useless, just taking some sort of input and turning into absolutely some mangled output without any way to turn it back, that seems useless, but that has so many uses in cryptography today. And it's one of the main reasons why stuff like internet connections and all, like when you connect to a website, stuff like HTTPS, right? Like these couldn't exist without hashing. Without the hashing algorithm, you could never connect to a website securely. HTTPS, by the way, what it does is it makes sure the only people who know anything about what's happening in the website will be you and the website. So if I was over here, right, me, and I'm watching YouTube, right, HTTPS makes sure that the only people who know what video I'm watching is me and YouTube. Nobody else listening in can ever know what video I'm watching. And stuff like hashing is incredibly important for these kind of things, because without it we could never have a safe, secure internet like this. And so that's it for today. I hope you enjoyed this video about me talking about hashing. And if you'd like to see more, comment by.